Good afternoon. In this video, we are going to talk about proposition 5 from book 2. So this proposition declares if we are given a finite straight line, for example, AB, and a point P that cuts AB into two equal parts, which means AP will be equal to BP, and another point Q cuts AB into two different parts or unequal parts, which means B will not be equal to C. This is B and this is C, unequal, okay? And then the proposition declares the rectangle contained by the two unequal parts, which means B and C, together with a square on the straight line between the equal parts and unequal parts, which means this straight line PQ. So this is the equal cutoff point and this is the unequal cutoff point. So the straight line between them plus, let's say it is D plus the square on this straight line will be equal to the straight line on half of this whole straight line, which means A squared. Okay? So let's give it a proof. So first of all, please recall proposition 46 from book 1, and let's just construct this square. So let us construct a square on a given straight line PB. And then very similarly, let us use postulate 1 to construct a diameter of this square by joining two opposite endpoints. And then from the point Q, let us apply proposition 31 from book 1 to construct a straight line that is parallel to the right side. Okay, they are parallel, and assume this parallel line meets the diameter at a point, and through this point let us construct another parallel line that is parallel to AB. Okay, and finally let us use proposition 31 again to construct a straight line through point of A that is parallel to the right side of this square. Okay, great. So we have finished construction and give them some names: A, B, C, D, E, F, G, H, I, J. Okay. So if you can still remember the proof in proposition 4, we have proved that if this is a square, then these two must be two squares, and these two complements must be two rectangles. We will just skip those proofs in proposition 5, okay, and assume we have already known the conclusion. So what? So please pay attention to this square. Let's say C square FB, and we know that square FB will absolutely equal to itself, and besides we know these two complements are equal because of proposition 43. We have proved it. So if we use combination 2 and add these two complements to both sides, we know that, let's say, complement square FB plus rectangle EQ will be equal to square FB plus, B plus rectangle FJ. Okay, because we already know. Let me just write it here. Okay, so this is equal to this. Great. And let's think about the square EB. Okay, so the left side FB plus EQ will be equal to another square, rectangle EB, and it is absolutely a specific parallelogram. And please recall proposition 36. If two parallelograms are in the same parallels and they have the equal base, then they are equal. So please pay attention to these two parallelograms. EB rectangle, or let's say here the base is equal to A, and this is also A because Q equally divides AB. So we know this parallelogram will be equal to this. So we know that EB is equal to rectangle or parallelogram DP, right? DP. So combine these, we can conclude that the rectangle DP will be equal to square FB plus rectangle FJ. Okay, so this plus this equals to this. Great. And then let's recall the definition of a nomen, which is definition 2 from book 2. If we subtract a very similar parallelogram from the whole, and the remaining 3 parts are called a nomen. So in this equality, let us apply combination 2 again to add dp plus, to add this. For convenience, let's mark it as R1 plus R1 will be equal to the right side FB plus, let me mark it R2 plus R1, right? And what is this? This is a nomen, right? This is a nomen here of this parallelogram. So let's call it nomen, just call it G, okay? This is G. Oh, sorry, we already have the point G. So nomen, let's call it nomen EBI, okay? So they are equal, right? dp plus R1, and so let us just add. Think about this little square. It's a square, so we can, if we add the little square to the nomen, so EBI plus the little square, let's call it HF. That will be the complete square, right? Square HB. And the left side will be dp plus R1 plus square HF, correct? And this is the left side, this is the right side, so they are equal because of combination 2. We add the same thing to both sides, so we know that square HB will be equal to rectangle DP. For convenience, let's call it R. Will be equal to R plus R1 plus the little square HF here. And how can we express them? So the square HB is absolutely A square, right? The side is A, and the rectangle here is equal to, let me check, AC, okay? Because this is a square. By the definition of a square, it is equilateral. So this angle, sorry, this side must be C, and this is a parallelogram. The opposite sides are equal, so this is C. So R will be equal to A times C plus R1, it will be C times D plus the rectangle, sorry, the square HF, which will be D square. So we have proved this, and what we are trying to prove, BC. Okay, so it is, let me check, the little square plus, okay, sorry. So these two squares, let's just combine them, R1 plus R2. If we think about the whole square, the one side is C and another side is A plus D, which is absolutely B. So the sum of these two squares are equal. equal to BC plus D squared. So we have proved that the square on the half will be equal to the rectangle by two different parts, part 1, part 2, okay, by them, plus the little square on the straight line between the equal cut point and the unequal cut point. This is the conclusion. So the proposition has been proved. Okay. In the next video, we are going to talk about proposition 6 from book 2. Thanks for watching. Have a good day.